Okay, so this is to go over your warm-up to make sure that you understood what you were doing, so get you ready for your quiz. So let's do this one first, 10.4. Okay, so find the measure of the indicated angle or arc in circle P. So we know P is the center. Given arc LM, the measure of arc LM is 84 degrees. And the measure of arc KN somewhere. So we know from K to N is 116 degrees. Okay. So then we want to find the measure of angle JKL. So I'm going to outline that. JKL. So remember, you ask yourself, where's the vertex? Well, the vertex is on K. So then if you follow it, the arc that we have is JML. Well, notice JL, the endpoints of this angle, are diameter. So how many degrees is arc JML here? 180. So remember, when the vertex is on the circle, you take its arc 180 and divide by 2. So that's 90 degrees. It's the measure of that inscribed angle. So let me erase that now. Okay, so next we want the measure of angle MKL. So M to K to L. So again, you ask yourself, where's the vertex? Well, K is on the circle. Excuse me. So you find its arc, which is ML, which is 84 degrees, and divide it by 2. So 84 divided by 2 is 42 degrees. Okay, so next we want to find KMN. So KMN. So notice its arc is KN right here, which we knew it from the given is 116 degrees. The vertex for this angle is on the circle. So I take 116 and divide it by 2. So what does that give me? 58 degrees. Okay. Now the last two are asking us for arc measures. So let me get rid of that. So now we want the measure of arc MJ somewhere right here. Well, remember, we've got a semicircle right here from there all the way from L, M to J. We know from L to M is 84 degrees. So we would do 180 minus 84, and that would give us the measure of arc JM, this minor arc here. So that's going to be 96 degrees. All right, and the last thing we wanted was the measure of arc LKJ. So where are we? L past K to J. Well, J and L, the endpoints of that arc, are endpoints of a diameter. So it's a semicircle, so it's 180 degrees. So that one just focused on your inscribed angles and just knowing your arcs. A review from 10.2, I think is where we did the arcs. Okay, so on this one, it's like what we were doing on your last example on notes. So measure of angle 1, let's do all the givens. So O is the center because it says circle O. A, B, C, D, and E lie on the circle. Segment BE is a diameter. Line AH is tangent, so A is the point of tangency. Arc AB is 50 degrees. I'll put that there. Arc BC is 70 degrees. And arc CD is 80 degrees. Now, like I did before, I'm going to find the other missing arcs first. We're missing AE and ED. Well, since BE is a diameter, then I know that this whole thing here has to be 180. So then what does the measure of arc DE have to be? 30 degrees. Okay. Then we also, you could add all of these up and subtract them from 360, or I'm going to use the fact that, change colors here. That I know this arc right here has to be 180 as well because it's a semicircle. So I can do 180 minus 50, which gives me 130 degrees. Okay. Oops. Let me erase. So now I have all the arcs that I need. So write that. There we go. Might be a little easier. Sorry, bear with me here. All right, so measure of angle 1. So angle 1, the vertex is on the center. So remember, we ask ourselves, where's the vertex? The vertex for angle 1 is on the center. So you should have gotten that the measure of angle 1 is just 70. It has to be the same as its arc. Okay, angle 2. Angle 2, the vertex is on the circle. So when you follow that angle, its arc is arc AB. So remember, when the vertex is on the circle, you take the arc divided by 2. So angle 2 should have been 25 degrees. Okay. All right. On the next one, we need angle EAD. Angle EAD right here. So the vertex is on the circle. So its arc is 30 degrees. So 30 divided by 2 is 15 degrees. All right. Angle 4 is right here. Now on angle 4, the vertex is inside the circle right here. And it's not on the center. Angle 4 vertex is here. So its arcs are 30 and 50. So you add those and divide by 2 when the vertex is inside. So 80 divided by 2 is 40 degrees. Okay. Then we have angle BAH. Change colors here. Angle BAH. BAH is this angle here. The vertex is on the circle. So its arc we take, which is 50, divided by 2. So that's 25 degrees. There's a bunch of stuff here. Okay. So then now we have BAH. So B to A to, oh, I already did that one. I want EAB. E to A to B. So then it goes with this whole arc here, which is the 30, the 80, and the 70, which is 180 when you add those up. So since the vertex for this angle is on the circle, I take the arc 180 divided by 2, so that's 90 degrees. Okay. Then angle CFA is next. So then C to F to A. So this vertex is outside the circle. So its arcs are this one, DE, and this arc here, which is the 70 and the 50 together. So this whole arc together is 120. That's what this whole arc is when you add the 70 and the 50. And we're going to subtract 30 from it. So we would do 120 minus 30 divided by 2. So that 90 divided by 2, so then that would be 45. Okay. Then we have that 120. So remember, this is 50. I got erased a little bit. EAG. So EAG, the the vertex is on the circle, so its arc is 130, so its arc divided by 2, which is 65 degrees. 130 divided by 2. Then we have angle 9. Vertex is on the circle. If you follow it, it also goes with that 130. So the vertex is on the circle. 130 divided by 2 is 65 degrees again. So remember, when two angles have the same arc in common, two inscribed angles have the same arc in common, then that means that they're congruent angles. All right, and then the last one, CDA. So where's that? CDA. So again, the vertex is on the circle. Its arc is the 70 and the 50 together again, which was 120. So you take the arc divided by 2, which is 60 degrees. So hopefully you got most of those right. These two warm-ups are very similar to what your quiz looks like. You'll have a front and a back again, so it'll look very similar to 10-4 on the front and similar to 10-5 on the back, where you have one that's a little more involved. Okay. All right, so now clear off your desk except for a pencil and a calculator. Put your dividers up and get ready for the quiz. So sub can pass out the quiz at this time. Pause. When you're done with the quiz, you'll restart this up for the notes. Okay, so today's notes, we're going to cover sections 10.6 and 10.7. So for 10.6, here is the central question. How do you use each of the 3 theorems to find missing segment lengths? So we're going to step away from angles for a little bit, like what we did yesterday, and we're going to focus on some different segment lengths other than the radius and diameters that we can find in chords. So segment lengths of circles is our only main idea for section 10.6. So you guys pause whenever you need to. So the first theorem is called the segment of chords theorem. So basically it's when you have a picture like what I have here. So instead of writing out all the word part, I'm just going to write out equations to help you with the pictures. So if you had a picture like this, where you have 2 chords that intersect inside the circle. Now, it's not like angles. We're not going to add the arcs and divide by 2. We don't care about the angles and arcs right now. We're doing segments. So what you're going to do is AE, whatever the length of AE is, you're going to multiply that times the other piece of the chord, EB, and that will equal the length from E to D times the other piece of that chord, EC. So you take the same chord and the 2 pieces that it got split into, and we don't know that those pieces are equal. They're actually not, okay? Then what we do is we take each piece, so AE times EB, whatever those are numbers, whatever those lengths are, equal to the other pieces multiplied together of the other chord, ED times EC. And remember, those are numbers. And then you can solve for whichever one's missing. So like one of those 4 pieces would be missing, so you'd have an X in there to solve for. Okay. All right, the next one is what we call segments of secants theorem, because you got some segments inside your secants. So notice that EB and ED, those segments are secant because they intersect the circle, and part of that secant is outside the circle. So that's why it's a secant, not just called a chord, because E is outside. Then here's what that says. It says if you take the outside piece, EA, and times it by the whole secant, EB, whatever these numbers represent, that's going to equal the outside piece of the other secant, EC, times the whole secant from E to D. So basically what you're doing on both of the secants is that red piece is the outside piece. You're going to do outside piece times the whole secant equals the outside secant times the whole. That's what you're doing on both sides. taking that outside segment times the whole secant segment and setting it equal to the outside piece of the other secant and the whole secant. And again, one of those will be a variable, so you'll have a variable in there that you'll have to solve for. So that's the segments of secant. Outside piece times whole piece equals outside piece times whole piece of the other secant. Okay. All right, and the last one is called the secants of tangents. Okay, so you've got a secant and tangents theorem, segments of secant and tangents theorem. But I don't care if you know the names or not. The names just kind of help you figure out what you're doing. But you've got a tangent, segment EA is a tangent segment, and you've got a secant ED. Okay, so what this says is if I take the tangent squared, that is going to equal the secant stuff, the outside piece EC times the whole piece ED. So if I were to write it like I had before, it would be the tangent segment squared, and that's going to be equal to the outside of the secant times the whole secant. That's what we're doing in general when you have a tangent and a secant. So you take the tangent segment, square it, and that's the reason why it's squared is because the outside piece and the whole piece of the tangent is the same number. So you're still kind of doing outside times whole, but the tangent outside and the tangent whole is the same number. So tangent squared equals the outside of the secant EC in this picture times the whole secant ED in this picture. Okay. So go ahead and glue in the examples that look like this. And this is for section 10.6. Okay, so each of these is showing you how we would have to use each of those, or how we could use each of those theorems to help us solve for this missing segment piece. Okay, so for example 1, part A, notice it's two chords that are intersecting, so it's the first theorem. So we take each piece of the chord of the same chord. So I would do 3 times x, because that's part of the same chord, and then I would equal it to the pieces of the other chord 4 times 6 multiplied. That's how that is. So then that's 3x equals 24, and then when you divide by 3, x equals 8. Done. They just asked you to solve for x. Okay. All right, on part B. So remember, this is where we take the outside piece times the whole piece. So what's this whole piece going to be? 9 plus 6, which is 15. And that's going to equal this outside piece times this whole piece, which what would this whole piece be? X plus 5. You're not multiplying. It's not 5 times x or 5x. It's x plus 5. That's how we got the 15 on the other side. So we do outside piece 6 times the whole secant 15 equals the outside piece 5 times the whole secant, which is x plus 5. So that's how you use the geometry to set it up. Now it's an algebra problem. Okay, so we're going to multiply that out. So what's that? 90 equals 5x plus 25. So you got to distribute to both. Subtract your 25. So is that 65 equals 5x. Divide it out. Is that 13? Yep. So that's x. All right, so that was the second one. That's when you have two secants. You take the outside piece times the whole equals outside times whole. This is one where you have the tangent, which is your 7. So remember, you do tangent squared equals your outside piece 5 times the whole piece again, which is x plus 5 again. You add those two numbers. So what do we get? 49 equals 5x plus 25. So we distribute again. Minus 25. So we get 4. 24 equals 5x. So when we divide, we're going to get, it goes in there, 4 times, so it would be 4.8. That's okay if you get a decimal. Or I would take 24/5 if you left it as 24/5. That'd be okay too. Okay, so that's an example of each of those, how you would use those. Okay, all right. Now we'll do section 10.7, and actually this is all review in section 10.7. So go ahead and just copy this essential question and your topic. Given the equation of a circle, how do you identify the center and the radius of that circle? So remember, this is the standard equation of a circle, so you can go ahead and pause it just to refresh your memory so it's here with your chapter 10 notes. But you have your parentheses x minus h squared plus the parentheses y minus k squared equals the radius squared. HK, remember, is the center of your circle. And it's always opposite of what it looks like in there because you have minus signs inside there. So if it was x minus 3 in parentheses squared, then the h would just be positive 3. So remember that. Okay, so you can go ahead and glue in the last examples. Let's start like this. Maybe. So these were the two that we mainly talked about. So example 1, identify the center point and radius of the given circle. So I'll just use capital C for the center. What would the center of this be? -1, +2. Because h would have had to have been -1, so that when you plug it back up in here, it would have been x minus -1, which is why it then became +1. So remember, it's opposite of what it looks like. And then what's the radius going to be? Because we know radius squared equals 100. So if you square rooted that, radius is 10. You don't have to show that square root piece. I was just showing you from this part of the equation. We knew that in this it was 100, and so you square root it to get the radius. Okay, so go ahead and pause it and try example 2. See if you can take the center and radius and write the equation. Okay, so you should have gotten, in parentheses, x plus 2 squared plus y minus 5 in parentheses squared equals 49. Okay, and remember, this is the one, if one of them was 0, like if that was 0, 5 for the center, then you would just have x squared with no parentheses since the h value was 0. So remember, always simplify it down as much as you can go. Okay, example 3 we didn't formally talk about before. We'll talk now. So the point 3, 4 is on the circle and the center is at 1, 4. Write the standard equation of the circle. Okay, so we have the center. No, that's at 1, 4. But what we're missing is the radius. We do need the radius, but we do have a point on the circle. So if I just kind of sketched, I'm not even putting it on the coordinate plane. We know the center is at 1, 4. And we know that there is another point on the circle at 3, 4. So if I connect that, that distance is going to be my radius. So what do you think I would do in the coordinate plane to figure out how long that is? What could I do? We've actually got a couple of choices. You could first start out by putting in your center. So you could say this is x minus 1 squared plus y minus 4 squared equals r squared. We just don't know what that is. Now you could put in the other point, 3, 4, this in as your x and this in as your y into this equation, and that would tell you what r squared is. So I could do 3 minus 1 squared, because that's the x value of this point here, plus the y value, which is 4. So 4 minus 4 squared equals r squared. Well, 3 minus 1 is 2. 2 squared is 4. 4 minus 4 is 0, so that's 0 equals r squared. So your r squared equals 4. So all I have to do now is come back. I already have r squared. You can figure out what r is. R is 2, but you don't have to because you need r squared for the equation here. So now all I have to do is come erase this r squared and put in 4 because that's what we figured out the answer is for r squared. The other ways you could have just done straight distance formula, but basically that's what you're doing here when we plug it into that equation. Okay. Now on this last one, it's graphed, so you just figure out where your center is. So there's your center. And then we'll count over to see what our radius is, which we can see is 2 because it's all going by ones. Make sure you read your grid so you know what it's going by. So then for example 4, what's the center point? What's that? 1, 2, 3, 1. And the radius, when you just count, and I would just do the straight across one. I wouldn't try and do some weird diagonal one. Why not do the easy part? And now you just write it out. That's the equation of that circle in the graph. So section 10.7 is just a review. The only new 2 pieces, I guess, is we're looking at example 3, where they give you the center and a point on the circle. You got to figure out the equation, or like example 4, where they give it to you in a graph. And you got to figure out the equation, but it's not hard to find. Okay, that's it for notes. You have a worksheet, 10.6, 10.7 worksheet. It's on OneNote, or you can get a hard copy. There's enough for everybody to have a hard copy if you would like. Okay, so you'll have a quiz over 10.6 and 10.7 on Monday.